So last week we started talking about how to do inference with proportions. And the first chapter, chapter 16, talks about how to do it with one sample, which means we just have one data set from some group, some area, and it's binomial, which means it's counting the successes of something occurring and the failures of something occurring. So 1 equals a success, 0 equals a failure. So your book uses an example of maybe some sort of medication trying to cure a disease. 1 would be curing the disease, 0 would be not curing the disease. And we talked about how to calculate the z statistic. I showed you how to do that in Excel. And I just followed along the example on page 402, and to calculate it, just a quick explanation in case you kind of missed some of that information. The z statistic is calculated with the sample proportion, so the proportion you've actually seen in your data set. So I believe in that example it was 0.289, and the hypothesized value, which is what that 0 means, right? It matches up with our null hypothesis. The hypothesized value was that p would equal 0.21, and so that was our hypothesized value. So we would plug that in here. And then the standard error was calculated using information from our sample, such as our hypothesized proportion, the inverse of that hypothesized proportion, and the sample size. So QO is just 1 minus 0.21, and N is the number of data points, which would have been 57. So the way we would solve this is, I always want you to set it up the way your book does, so I want you to state what your hypotheses are. So the alternative hypothesis was that the proportion will not equal 0.21. The null hypothesis was that the proportion will equal 0.21. Okay, now we calculate our test statistics. So first we would solve the standard error. We would plug these values in. To our standard error of the proportion formula. So equals the square root of 0.21 times over 57. 1 minus 0.21 is 0.79. And then you would solve, so you would multiply these two together, then divide by 57, and then square root it, which should give us 0.05397. I highly recommend working to at least 4 decimal places to ensure that your data is accurate. If you only round to 2 or 3, you're going to have some rounding errors in your calculations. So once we have the standard error of the proportion, we can calculate our z statistic. Our observed proportion divided by standard error equals a z-stat .63. So always make sure you solve the numerator and denominator separately. So I would subtract those first and then divide. And you get a z-statistic of 1.63. So how do we find the p-value for that? Again, that's going to be in your F table. So let us find it. Oh, and we should have stated our alpha level at the beginning. So I'm going to turn to the table in the back of the book. And I'm going to hold this up higher because I don't think I did a very good job in the last video. So we're looking at the z table. We're going to try to find 1.6 right here. And then we're going to look for 3. So this is the column of 0. So this would be 1.60, 1.61, 1.62, 1.63. P-value of 10.310. 10. Now we compare that to our alpha value. This is how we make our conclusions in hypothesis testing. So we say our p-value compared to our alpha value. Well, our p-value is slightly larger because it has some additional numbers out here. It's slightly larger than our alpha value. So the rule of thumb is if your p-value is greater than alpha, you fail to reject the null hypothesis, which means we don't have sufficient evidence to conclude that the proportion is different than 0.21. If our value was less than alpha, we would reject the null hypothesis, which means that our data suggests that there is a significant difference between p and the proportion and 0.21. So that was just a quick rundown from last week's discussion. And this method uses the standard normal distribution, which is why we're able to look up the p-values in the back and draw conclusions. However, there are rules that say you can only use this method if you've satisfied the NPQ rule, which is that n times p times q should be greater than 5, greater than or equal to 5. Well, that doesn't always happen. Sometimes they're not equal. So in that case, we have to use the exact binomial method. So let's walk through one of those examples. So I'm going to walk through the example in chapter 16 on page, starts on page 404. So this example is using a sample that is small, and we must use the exact binomial distribution method. First, we'll state our hypotheses. So our alternative hypothesis is that our proportion will be greater than 0.5, and the the null hypothesis is that p will be equal to 0.5. So this is the first step. Then we calculate our test statistic. So what do we need to calculate our test statistic? Well, the nice thing about the binomial method is that x equals the frequency with which the event occurred in our data set. So in our data set, our data looked, for this example, was 1, 2, 3, 5, 6, 0. We had 8 observations, so n equals 8, and 6 of those resulted 1, 2, 3, 4, 5, 6, and a success. So our test statistic is just 6. Awesome. Test statistic is way easier in this method. However, calculating our p-value takes more steps. So to calculate the p-value, we have to use the formula in the book, and we also have to know how to calculate what's called the binomial coefficient, which is that c value you see in your book. So first, let's talk about the binomial coefficient. The binomial coefficient is c for n, which is our sample size, and x, which is our observed success rate, equals the n factorial, x factorial, and minus x factorial. And factorials are just a really fancy way of taking the original number and multiplying it by 1 less, multiplying it by 1 less, multiplying it by 1 less. So what does that mean? Then it would be, let's say if our n equals 4, n exclamation mark would equal 4 times 4 minus 1, which is 3, times 3 minus 1, which is 2, 2 minus 1, which is 1, all the way down to 1. So if n equaled 8, it would be a lot more. We'd start with 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So n exclamation point when n equals 8 looks like this. So for our example, we have an n equal to 8 and a c and an x equal to 6. So we would have 8 exclamation point divided by 6 exclamation point times 8 minus 6 exclamation point. So what this would look like is our numerator would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 6 times 5 times 4 times 3 times 2 times 1 times 8 minus 6, which is 2, times, and we have to do the factorial of that, so 2 times 1. Multiply those together, and we get a numerator of 40,320 divided by 1,440, which equals 28. So for our p-value, we have our first binomial coefficient, 8c6 equals 28. But we're not done, because for the p-value is the probability of x being greater than or equal to 6. So we have calculated the coefficient for x equaling 6, but now we have to do the same thing if x equaled 7 and x equaled 8. So what that looks like is the same logic follows, and I'm not going to do all of it, but we'll just go ahead and do a short example. So our sample size stays the same and is still 8. The x value changes to 7, so we still have 8 as our numerator divided by 7, n minus x, so 8 minus 7. Again, the numerator is 8 times 7 times 6 times 5 times 4 times 3, 1 divided by 7 times 6 times 5, 4, 3, 2, 1 times 8 minus 7 is 1 for that, and that'll give us 8C7, which is equal to, let's see, your book has it, 8. And then the same logic follows for our final condition, where if x was greater, if x equaled 8, that would also be greater than or equal to 6. Same logic. This one equals 1. Okay, so now we have almost all of the values that we need to calculate our p-value. Hopefully you understand the binomial coefficient a little bit better. So the next thing we need to calculate our p-value is our p observed, which we already know is 6, and then we need the inverse. Oh, sorry, we need our hypothesized p, which is 0.5, and we need the inverse, which is 1 minus 0.5, which would be 0.5. So now that we have all of that, we can actually calculate the probabilities of obtaining the different x values, and then we can multiply all of them together to get the p-value. So let's go ahead and do that. So probability of x equaling 6 equals the coefficient for the sample size of n equals 8, x equals 6, times our null hypothesis p-value raised to x, 6, times the inverse raised to 8 minus 6, or n minus 6, right? Sorry, n minus x. And the probability of that is 28 times 0.0156 times 0.25, because this becomes 1/2 raised to the 2, which is 1/4, equals 0.1094. We do the same thing for the probability of x equaling 7. Be aware that these values are going to change, because now we're looking at it if our x value equals 7, 0.5 raised to 7, 0.5 raised to 8 minus 7, which becomes 1, which means nothing happens, it stays 1/2, equals 0.0313. And same logic, but now for the last possible condition in which x would be greater than or equal to 6 is 8. Same logic, this would change to an 8. This would drop out of the equation because 8 minus 8 is 0, and we would end up with 0.0039. Now to calculate the p-value, we add all of these values together. That gives us a p-value of 0.1446. Now, we get to use the same logic we've already used. We compare our p-value to our alpha value. Our p-value again is greater than alpha, so we fail to reject the null hypothesis. And that's our conclusion.